Alright, today we will talk about Gurobi Optimizer. And let's start by setting context. Now, Gurobi is a commercial optimization solver designed for large-scale mathematical optimization. When people talk about linear programs, mixed integer programs, or quadratic programs at industrial scale, this is usually the reference point. The solver is built to handle very large models reliably, and the focus is on solving them fast, repeatedly, and with predictable behavior. That combination is why it shows up in production systems rather than only research code, and that's important. So here, here's the guiding idea behind this system. Now, from the beginning, the solver was built for modern hardware. That means multi-core processors, parallel execution, and distributed environments are treated as first-class concerns rather than afterthoughts. On top of that, the algorithms reflect decades of optimization research, but they are implemented with careful attention to numerical behavior and robustness. The outcome is that the same model that struggles elsewhere when often solves cleanly and consistently here, even when the scale grows. And why Gurobi? Here, let's talk about why this solver tends to be chosen in practice. In optimization, time matters in a very concrete way. A model that solves in seconds can be embedded in a decision loop. A model that takes hours usually cannot. Performance here is not a marketing detail. It changes what kinds of decisions you can automate. Our many independent benchmarks, this solver tends to be near the top, and that reliability is what earns trust for teams deploying optimization in real systems. Okay, now uh, here some metrics. Thousands of enterprise users rely on the solver speeds up. Our alternative approaches are common, and the development team brings decades of combined experience, and the solver integrates with a broad range of programming environments. So each of these points connects directly to whether a tool fits into a production workflow. So here are some traditional challenges. What are they? It helps to contrast with these common problems in older or less mature solvers. Large models can take a long time to solve. Scaling can break down as variables grow. Numerical instability can lead to unreliable answers, and APIs can become awkward to work with. Parallel execution is often limited or difficult to control, which wastes available hardware. And what are Gurobi advantages here? The corresponding strengths address those issues directly. Performance is a primary design target. Scaling to very large variable counts is routine, and numerical handling is stable across a wide range of models. And the Python interface in particular is designed to feel natural when building expressions and constraints. So support spans linear, mixed integer, and quadratic formulations, and multi-threading is built in rather than bolted on. And what are core components of Gurobi here? Thinking in terms of components helps clarify what happens when you call optimize. Now we have an architecture here. At the top of is the model builder, where variables, constraints, and objectives are defined. Once the model exists, a pre-solve engine simplifies it. This includes reducing redundant constraints and tightening bounds, which can dramatically shrink the problem before any heavy computation starts. After that, the core solvers take over. Linear problems use simplex or barrier methods. Mixed integer problems rely on branch and bound with cutting planes, and quadratic problems use interior point techniques. So throughout this process, parallel execution is used whenever possible, and multiple high-quality solutions can be retained in a solution pool. Okay, now some modules here. To work with all of these programmatically, the Python interface exposes a small set of core objects. Now, Gurobi model. The model object is the central container. It owns variables, constraints, objectives, parameters, and the source code itself. Everything flows through this object. And variables represent decisions. They can be continuous, integer, or binary, and they carry bounds and coefficients that participate in expressions. And constraints encode relationships between variables. They support equality and inequality forms and expose information like slack values and dual values after a solve. Okay, and expressions here are how objectives and constraints are assembled. Linear expressions handle sums of variables, while quadratic expressions allow subtract terms and interactions between variables. These objects exist so that large expressions can be built efficiently and manipulated safely. That's okay. And here GRB, the constants module holds solver-wide definitions. This includes variable types, status codes, and parameter names, which gives models explicit and readable. Okay. Here we'll talk about some key capabilities. With those building blocks in place, the solver supports a wide range of problem types. And linear programming handles very large continuous models. Mixed integer programming uses advanced branch and cut techniques with heuristics and parallelism. Quadratic programming supports both convex and certain non-convex formulations. There is support for multiple objectives, solution pools, infeasibility analysis through irreducible inconsistencies subsystems, and warm starts that reuse prior solutions to speed up future solves. And here, workflow. Look at this. Let's put these into a workflow perspective. Now, a typical pipeline starts with model building, where variables and constraints are defined. Presolve then simplifies the formulation. Optimization runs the appropriate algorithms. After that, solution extraction pulls out variable values. Analysis follows using sensitivity information or dual values to understand behavior. And finally, the results are deployed into a production system where decisions are executed. And some applications, as you guess, these capabilities show up across many industries, and in supply chain and logistics, models handle routing, inventory, and network design. In energy systems, optimization supports grid operations, unit commitment, and trading. Finance uses it for portfolio construction, risk control, and asset liability matching. So here, manufacturing relies on it for scheduling, cutting stock, workforce planning, and quality control. The common thread is large, structured decision problems that must be solved reliably. So look at that ecosystem. The solver, Gurobi, fits into a broad ecosystem. It integrates with Python, C, and C++, Java, .NET, MATLAB, R, and Julia. It also connects to modeling tools such as AMPL, GAMS, Pyamo, JUMP, CVXPy, or OR tools, and it reads standard formats like MPS and LP. So that flexibility matters because it allows teams to keep their preferred modeling environment while relying on the same underlying solver.